My name is Emily Gallagher, and I'm happy to represent this SPIE talk. It's always great to get a larger audience, especially when you're talking about the climate. So I will be talking about transformation, climate-aware IC manufacturing, and I'm presenting on behalf of the Sustainability Semiconductor Systems and Technologies at imec. In the contents of the talk, I'll first speak about environmental awareness for those of you who might be uninitiated, introduce planetary boundaries for safe limits to ecosystems that are being crossed, and talk about IC manufacturing and how we have a significant and growing role in that. And then the bulk of the talk will focus on transforming into an industry that has less impact. So that involves quantifying the environmental impact in semiconductor fabrication, executing climate-aware process development, and I'll provide examples of that. And then finally, circularity and what role that can play. And to make it easy to internalize, I'll provide a summary that includes actions, corporate benefits of those actions, environmental benefits, and then ideas for removing barriers that might be in the way of implementing those. And then to make things a little more interesting, I wanted to leave you with a quote to consider during the talk, which is, "Even the smallest person can change the course of the future." And I'll leave it to you to think about who those eyes might belong to. So starting with the introduction. The Earth is warming, and there are lots of ways you can see this or maybe perceive it in your own daily experience, but I tend to go to some data. So here is daily global surface to air temperature. So it's temperature, each gray curve represents a year going from January through December. So you have the typical this is in the northern hemisphere, so you see the standard that you would expect with higher temperatures in the summer. But what might not be as anticipated are the extra curves that are highlighted. So the dashed line is the 1991 to 2020 average, and you can see the last full year, 2024, and 2025, well above the curves. So clearly showing a warming trend. And then you can go also to water. So here it's from the same website, but you can look at the daily average. I chose one that was pretty close to SPIE relative to the baseline, and you can see that the sea temperatures are also getting warmer. But it's not just climate. There are other planetary boundaries. So there is a framework that was developed to define science-based safe operating space for humans, and it divided into all of these boundaries. So you can see climate here, but also pollution, ozone, aerosols, etc. All of them that are red have actually been crossed. And as I mentioned, climate is really only one of those impacts. So going a little bit further into the planetary boundaries, and I won't stay too long on this part, but the semiconductor contributes to many of the categories. So when you're thinking about climate, we use process gases that have very high global warming potential, much, much higher, like thousands of times higher than CO2. We use novel entities that contain things like PFAS and microplastics, and we introduce toxic chemicals and heavy metals. So there are many of these boundaries that we contribute to. And in addition to that, the global chip market continues to grow. So that's a great thing for a lot of our job security. If you look at the market in 2021, it was at 590 billion. Going into projections towards 2030, we're going to exceed $1 trillion. So the growing demand for semiconductor chips really is driven by data centers, wireless communication, automotive, etc. And with that growth comes increasing emissions. So we see that here in that currently we have about 37 billion tons of CO2 equivalent. Actually, that is even a little bit outdated, a couple of years. And ICT industry is 2%, with IC manufacturing being at just under 200 million tons. And then there's AI. So I mentioned AI deployment. It's growing exponentially, and that's as a result of model training, data centers, and power consumption. If you look at operational emissions, which is what everybody talks about, it's all the energy that the data centers are going to use. It's about 70% of the total But what's really interesting to me is the 30% that's embodied emissions. So embodied means IC chips, for example, the energy that's required to make chips that will go into the data centers. When we talk about data center consumption, we're typically talking about that 70%, but we as an industry can have a large influence on the 30% that comes along with it. So we really need a standard, reliable method for reporting and minimizing the embodied impact to AI. And that's what I'll shift to now. So we have developed methods for quantifying environmental impact from the fabs view. And your viewpoint is really important when you talk about environmental impact. So a life cycle assessment of IC manufacturing using the virtual fab is what I show here. This is a methodology that has been established in other industries, but basically it involves a lot of interpretation. There's a goal and a scope. You come up with an inventory of what you're using, and then you assess its impact. And throughout all of this, of course, you have to interpret results. So it's important to think about what our viewpoint is. So basically, we're talking about IC manufacturing. So I've got a fab indicated here, but we also have to consider the materials, the refinement of the materials that go into the fab. And then potentially you can include packaging. And then there's the use phase and end of use, potentially recycling. I won't really touch on the use phase because we don't have a lot of specific information on it. I'm really going to focus here on the fab and the incoming materials. So we have developed this virtual fab. It's not supposed to be any specific fab, but representative of a high volume manufacturing fab. And to do that, we have detailed knowledge of tools, of processes, and of materials. And then it's important to be able to put those together into process flows. So whether they're logic or memory or packaging. And then in addition, we need an understanding of the fab models. So for example, how many tools you would need to keep full capacity, what kind of uptime on the tools, what type of abatement is used, what the die size and yield expectations are. So all of that is rolled in and generates, first of all, an inventory. So really what is used to make an IC chip. And then that's not good enough because you also have to know what the impact is. So for example, if you use a certain process gas, you want to know what the global warming potential of that gas is. And there is a standard for that, EF 3.1, that we apply. And so putting these two things together, the inventory and the impact, we're able to get the environmental impact of IC chip and system manufacturing. So it's parametric and it provides a proxy for the manufacturing itself. So the advantage of this bottoms-up methodology is that the results have granularity. So you can identify high impact steps. They're actionable. You can check sensitivity and the results can be projected. So you can pathfind towards future nodes and make decisions about where you want to go that might have lower impact. And throughout this, I will show a number of results from using this virtual fab called imec.netzero. And I tend to put some of the details that some people might be interested in a gray box. So you'll see something that looks like it here. If I don't actually state it, the N2 is the logic node that I'm using. I tend to take an industry average for the carbon intensity of the energy used. So whether you're using, say, coal-based energy or oil-based or nuclear. Nuclear is actually very low carbon intensity or renewables of some kind. And what type of abatement is used. And also the volume of the fab. So 60K wafers per month is sort of a standard that we use. And then expectations about yield and die size, I kept those all constant. So before I go into a lot of more detail, it's important to talk about the definition of emissions, and there is a greenhouse gas protocol for that. Basically, it's included in all of our current models, and the things that aren't included, I'm going to put in a gray box. So these are greenhouse gases that are commonly known. They are the result of this in the atmosphere. This is what the cartoon is supposed to mean. They're the result of scope 1 emissions. That's one type of emissions, which are direct emissions that come from burning fuel or escaped gases or high temperature transfer fluid, heat transfer fluids, process gas emissions. We could include company-owned vehicles, but we don't. Scope 2 is the carbon that is generated to produce electricity. And scope 3 is really everything else. For us, what we focus on is the production of purchased materials, upstream electricity. We don't include the use phase or business travel. And notice that I've got some color scheme going here with the scopes. I'll stay consistent with that. So if you see a little red box in the upper right of a chart, I'll be talking about scope 1. Same thing for scope 2 or scope 3. So first of all, let's focus on energy. Scope 2, and when you talk about scope 2, that's a process that might consume a lot of energy. It tends to bring up lithography, and that's where I will go here. So scope 2 focus, and the reason is if you look at a baseline technology and climate impact lens, I'm comparing two technologies here. So N28, a more established node, and N2, which is kind of representative of the leading edge. And this is broken down into scope 1 emissions, scope 2 electricity, and scope 3 materials. And there are a couple of things that you can see here. Emissions increase with more advanced nodes, and that correlates with the number of process steps. It's about 2x. In terms of emissions. And the other thing to notice is that 60% of the emissions comes from scope 2 electricity. But then we can drill down further and break this scope 2. So this is only scope 2 for the advanced node, the N2 logic node. And you can see which ones take the biggest part of scope 2. So over 21% is from litho scanners. And then next comes dry etch, and then deposition. So patterning consumes an enormous amount of the scope 2 budget. And then looking a little bit more detail into the trends. So only looking at scope 2, and I'm normalizing everything to N28, but taking it through N7 node done without, and then with EUV, and then N2, which of course uses EUV. So a few things you can notice, this is broken down. So each color is associated with a different process area. So you can see which ones contribute the most. So first of all, when we go from N7 without to N7 with EUV, there's a reduction in the number of steps because you've eliminated some multi-patterning, and that reduces overall emissions. And the second thing to notice is that lithography in general has a huge, large and increasing contribution to the overall scope 2 emissions. So the question is, what do you do about that? imec not only developed imec.NETZero as a platform to assess, but we also work on processes in a real fab, 300mm fab, and develop them towards the future. And part of that development involves EUV dose reduction. And so I'm just going over here the knobs that we have for a holistic solution. You can work on your reticle and imaging, you can work on materials, and you can work on the process itself. Those are the knobs available to you. The example I'll show for today is a materials example and specifically photoresist. And this is work that was presented by Mihir Gupta at the conference. So the goal here is to reduce EUV dose to defectivity and characterize the impact in terms of CO2 equivalent. So that means you just take whatever emissions are generated and use this common unit CO2 equivalent for emissions. The work was done on a 0.33 NA scanner. The pitch was 28 nanometer, and the target was M2 layer for an imec N5 node. So if you consider 4 different resists, and this is just sort of a cartoon of the patterned resist on top of the layers, 28 nanometer line space. As you look at these 4 different resists, you can see this is unbiased line width roughness. So you want to reduce that as much as possible as a function of dose. So these different resists behave differently. And the idea being that if you were operating here on this green or even the purple resist and you shifted towards the blue one, you would have an 18% dose reduction. That was the function of a lot of work. It all looks very simple here. But in addition to reducing line width roughness, you also have to look at your failure-free latitude. So the limit for that is shown here. And you can see that this resist number 3 performs quite well. So we have a candidate that allows you to reduce your dose by 18%. Well, what does that do to environmental impact? Oh, I should have mentioned, there were a number of papers that all deal with dose reduction, and those references are given here if you want to look them up on the SPIE website. Well, we came up with a way, and this is the version 0 of what we called e-scoring. We have since updated it, and so will be newer versions presented in the future. But in this case, we selected 5 key impact or inventory parameters that have reliable data in our databases. Getting good data in order to do climate impact can be a challenge, so we wanted to restrict ourselves to places we had relatively high confidence. So what we focused on were climate change, ADP, which stands for abiotic depletion potential. It's a proxy for total material scarcity. So just think of it as material scarcity, and then water use. And we chose water drawn from the network. This tends to correlate with UPW or any other type of water. We report a test relative to a reference and then generate a percent difference for each parameter so that everything's in percentage and we can kind of put them on the same chart. And we use a spider or radar chart to visualize the impact. So this is the methodology, and I'll show it in a few examples, but starting with this photoresist one that I just explained. So here's a different axis for emissions, electricity, materials upstream, material scarcity, and water use. And you can see in the black dashed line is the process of record that, of course, is only relative to a self, so it's 100%. And you can see where this 18% dose reduction had an influence. So basically everything but water use was lower with this 18% dose reduction. And some of you who are familiar with photoresists might say, okay, that's great, but doesn't PFAS have an impact on climate? So I'm not going to focus a lot on PFAS here. One of my colleagues, Danilo De Simone, had a very complete talk on that. But what I can say is this methodology doesn't fall apart if we add more information. So for example, you could say hypothetically, well, I also reduced the amount of resist I used and PFAS is lower. So then you could just add another axis to represent that. And that's the nice flexibility of this spider chart visualization. So now we'll shift gears to direct emissions, scope 1, and that will push us towards abatement and dry etch discussions. So here is an advanced logic node, N2 node, and I'm showing total emissions, again, as a function now of carbon intensity of the energy. So industry average is a mix of all of the locations where fabs exist. And then US New York State, it uses a lot of hydropower from Canada. And so when you do that, you reduce the amount of scope 2. And so what we see is that using this lower carbon energy reduces the total emissions by 40%, a pretty large effect. And also, once you've done that, scope 1 begins to have more importance and obviously requires more attention. So if you do now a breakdown of just scope 1 emissions by process area, dry etch shows up as the dominant contributor. So the reason for that is a lot of greenhouse gases are used in IC manufacturing. And just as a review, greenhouse gases are those that absorb in the IR, trap heat, and are greenhouse gases. An important metric for those types of gases is called global warming potential, meaning it's always relative to CO2, so the amount of gas absorbed over time relative to CO2. So as I mentioned, a lot of the gases used in our industry are a lot worse than CO2, and you can see, as SF6 here with over 24,000 times the impact of CO2, meaning you release 1 kilogram of SF6, it's equivalent to over 24,000 kilograms of CO2, a huge multiplier. And what's important too is how long they live. So the 100-year global warming potential is a standard that's used. It means you wait 100 years and then you say how much more the impact is. So it's not like this is just for a month or something. It stays in the atmosphere for a long time. So if we now do a Pareto of process gas emissions as a function of process gas, clearly global warming potential is one component, and then the gas volume used in the process is another. And I should say this is without abatement. So this means you use a gas, it comes out, some of it comes out of your process. There are byproducts, those are all added together, and that's what's being reported here. This is assuming that you're not trying to burn them or get rid of them, you're just releasing everything. And so if you do that, you get a Pareto where CF4 dominates, and then NF3 is second and it goes down. With abatement, the numbers will change. And the reason for that is something called DRE, which is the destruction efficiency of your abatement system. So this means you're either burning or in some other way destroying the greenhouse gases before they're released. This DRE number is a maximum of 1 if they're completely destroyed, and then some fraction of it. So you can think of it as a multiplier. Excuse me. And important to notice that CF4 here does not have a very high destruction and removal efficiency. And I should say there's a standard for this, and it's called IPCC Tier 2C AR6, and so those are the values that I'm quoting here. Now, if you do apply abatement, the same chart on the left converts. A couple of things to notice. The y-axis has changed. It was a maximum of 300 kilograms CO2 equivalent per gas, and now it's 30. But the Pareto CF4 still dominates, and a lot of the same gases are still here. So you reduce the overall number, but there's still a significant contribution from these etch processes, but it's much better. So then, what can we do to reduce greenhouse gas emissions from processes? So to think about that, if you want to talk about the relative greenhouse gas emission as a function of the time to develop, there are a couple of things you can do. From the facility side, you can apply and maintain abatement, that destruction of the gases. And so you'll have a pretty short time to implement. You'll get a pretty large influence, but you'll always have some emissions associated with running abatement and or the byproducts. Then you could talk about process action, so optimizing existing recipes with the same gases. That's a lot faster to implement and has lower risk. But in the end, you'll still have some emissions there for the same reasons. And then the final thing is you can explore alternative gases. And this one takes the most effort to develop, but eventually you could go below, get to a point where you're in a better space than you were with either of the first two options. The challenge is that it often carries other burdens such as toxicity or explosion hazards or corrosion. And also a tremendous amount of energy was invested over time, energy meaning people engineering energy, to develop the best possible processes with the current gases. So there's a long learning curve to come up in order to match that. And there are some talks, this one from Air Liquide that were given at SPIE that we'll talked about that in more detail. What I'll provide an example of is optimizing existing recipes with the same gases. So I'll give you an example of this work. So the process that was developed really came from one fundamental etch observation. So this was an ICP plasma reactor. Inside is a plasma containing ions, neutrons, and photons, whose mission is to remove material in a controlled way. And as part of the development effort, we measured the gas residence in a chamber, measured with OES, optical emission spectroscopy. And so if the gas was injected just during this purple time, and then afterwards the signal was observed. And if you add up the area under the curve, you notice that 60% of the gas signal is actually from wall outgassing. It's present after your injection stops. So the question is, can you leverage this extra residence time? And we're only talking about seconds. It's not a long period of time. And so basically that process is called transient assisted process, or TAP etch. And we applied it to a 28 nanometer pitch, full stack. So we had photoresist patterned, and the idea is to transfer it down into the blue titanium nitride layer, which is the hard mask. So if you, on the right is a couple of different layers of the process schematic. So starting with the gas injection, the carrier gas, and then the reactant, and then looking at the density of the reactant in the chamber. So this is the pulsing region and then the decay. And then one cycle is the gas step, and then the sort of waiting step. And if you look at sort of what is used for gas 1 and gas 2, we've listed those out for each of the different layers that we're etching. So each cycle takes about 3 to 5 seconds, and the gases used for each one are shown here. And the process actually works. This is an example of top-down SEMs. The results really were equivalent to our reference process, less than around 5 minutes of processing time, going from this chemically amplified resist down to the nitride with an unbiased LER of about 1.4. But what about the climate impact? Well, one of the key missions was to use less gas. So what I'm plotting here is relative volume of gases for the reactive ion etch process of record in blue, and this TAP process, which is the experiment, in green. So what we did is design this process, and you can see that really did have a tremendous effect on the gas use in terms of 98% reduction on CF4 and elimination of the two other gases. What was unexpected is when we used our visualization of climate impact, we saw that the process of record here, should be at 100%. And this first version of TAP, which is actually shown in orange, was a longer process. It was much longer. And because of the length of the recipe time, it consumed more electricity, materials, and water. And you see that increase of the footprint. So with this larger impact, we don't feel like we have a good process yet. And we kept working on it. So in order to understand where to put effort, we looked at the time per step. I mentioned the recipe got longer. So this is time per step, same axis, y-axis. And we noticed that if we just isolated to this one amorphous carbon layer, the Rye process was much, much shorter than it was for this TAP hybrid. So we created a TAP hybrid process, which combined the reactive ion etch for just the amorphous carbon steps and left TAP for the other ones. And the question is, well, how does this hybrid process look? So if you go to the climate impact visualization, you see the process of record, our first attempt that was all TAP, and this new hybrid one that clearly has a smaller footprint. So it sort of gives you the advantage of looking a little bit holistically at your process changes to make sure you're not just shifting the burden from one area to another. So let's talk about materials now. You should be getting familiar with this chart. So it's total emissions, and then I sort of choose what I put here to bring up something different. I'm trying to focus more on scope 3, but I've given you some review. So 0% abatement, so no destruction of the process gases. As you move to green energy, you got to this point. But now, if we're looking at the abatement case, you see that the same trend shows when you have, greener energy, you reduce the overall impact. When you do that, it's important to also notice that scope 1 can be reduced by adding abatement. So it doesn't matter whether you're using green energy or not. In either case, you are able to reduce by adding abatement. But once you get to this final state with complete abatement and greener energy, you see that scope 3 is dominating. And so we need to pay attention to that as well. In order to do this, maybe consider the material value chain in the semiconductor industry. So you have tool manufacturers, IC chip manufacturers, the IC chip fabs, and then finally you have electronic product and use phases and end of life. Each of these segments has a material supplier, and they might be different types of materials, but they all play into it. And then in each case, you can consider both on-site recovery and reuse and off-site recovery. But one of the challenges is there's so many materials used. What's the best way to prioritize this effort? So we'll focus on the IC chip manufacturer and talk very specifically about one use case, which is the EUV scanner. So for that, there is an EUV source and there's hydrogen abatement. And it's important to know that hydrogen is an essential for both the source and scanner function, keeps the optics clean. And if you're going to think about a process from an environmental impact perspective, it's important to consider the inputs and the outputs. So photoresist is obviously one input, and it goes to waste. But there's also electricity that goes to each of the components of the system. And in the case of the EUV scanner, as I mentioned, there's also hydrogen gas, which comes in here, goes into the hydrogen abatement. It also goes into the EUV source itself. Both of those cases need to be abated, and that consumes energy. So at imec, we looked at hydrogen recycling unit to see what impact that would have. So basically what this does is it takes 70 to 80% of the hydrogen used in the EUV scanner and is able to recycle it back to reduce the total use of hydrogen. if we look at that from the climate impact perspective, the standard abatement is shown in black. And when you use this hydrogen recycling, you're able to reduce many aspects of your environmental impact. So recycling is clear, and this did include the energy required by the unit. So it's clearly an impactful thing to do. So shifting gears a little bit and talking about critical materials. So one thing, one incentive for looking at recycling is considering what materials are in fact critical, meaning that there could be a risk to supply. And this is not with the semiconductor industry in mind. It's just a paper that we're quoting here, and it splits up different chemicals by region, whether it's Japan or the US or the EU. And stars are next to these critical materials that are also consumed by the IC manufacturing. So one thing that's important to know is we're not the only industry, right? A lot of these are also used by growing sectors, so like electric cars or electrical networks or greener energy. So it's important to understand that the supply chain will become under stress, and this is a huge reason for worrying about recycling. So it's hard to do that without some level of priority. So what we did was developed an initial method. So a value is assigned to each circularity factor. These are the 6 factors, whether it's critical, how easy it is to recycle, if there's regulatory risk for the material, if there's any value to the material after it's used, what the embodied GWP, so how much emissions were generated to make the material itself, and what the mass of the material is, so all the volumes used. So all of these things are considered and given a weighting factor. In our case, we applied equal weighting, so that means that our larger value is a good candidate for circularity. And then we ranked the top ones here so you could see them. And important to notice, IPA, ruthenium, NMP, slurries, a lot of things are here that are important to our technology. And I should say this is just a very preliminary effort to try and give a better sort of quantification of circularity and what we should spend our time on. But there is an effort between imec and SEMI, a collaboration on material circularity, that is kicking off. So if you're interested, you can contact Lizzie Boakes from imec or any of the other people listed here. And the idea is to come up with a methodology for identifying the priority materials to help with recycling efforts. And, I had started off giving you a picture of 2 eyes and this quote, even the smallest person can change the course of the future. So I think it's important for us to think about our own individual actions, but also what industry transformational actions are. And in case you've had time to think of it, she was speaking to Frodo, the Hobbit. And so he's very small, but basically, able to make a difference. And so one way most of us have some influence is on yield. Yield always matters. And I think this chart shows that pretty clearly. It's using the imec.netzero platform to generate the data. It's for an advanced logic node and a HVM virtual fab with 60K wafer starts per month. So we show total emissions and the die yield from 100% to very, very low for both full field and a smaller chip. And in general, with full field, there's, it's harder, there's more unused silicon space when you do that. And that's why it always has higher emissions when you're full field. But the kind of things you could notice is you can kind of get a number out of what it would take. So if you assume the large die, which is in blue, and a 1% yield loss, it leads to about 20 tons of CO2 equivalent per month, which is comparable to what's allocated for not allocated, what a US person takes per capita in 2023 for 1.5 people. And I should say that target, that use is much higher than other geographies. And if you look at a per capita target for what the Earth can support, it's typically quoted as about 2 tons CO2 equivalent per year. So when you think about that, this 1% yield is a tremendous amount and something to focus on. So if you do anything at all with yield, you have an impact on climate. So what kind of actions can we take as an industry? So I've listed the actions here. I'll go row by row. So we can implement process efficiencies. The corporate benefits there include lower cost of materials and less use of electricity. The environmental benefits are similar, but you just think of them differently. So less use of materials means, you're not consuming water, you're not consuming electricity from other people and the generation of it, you're not using as many materials, you're not generating as much waste, and you reduce the overall climate impact and strain on the different ecosystems. We can also shift to low carbon energy sources. So that's the scope 2 I was talking about there. So there you reduce the carbon footprint, and that's really helpful for corporate marketing. If it's on site, you can also decouple from the grid, which can have a huge benefit. And in general, in terms of environmental benefits, that's reducing the climate impact. And then finally, looking for opportunities to reduce, reuse, and recycle materials. Obviously, that can help reduce dependence on the supply chain. It might become imperative if there are risk or geopolitically restricted materials. And of course, it generates less waste. And in some cases, the ROI is good on this, and over time, you will actually reduce costs. But then there are always barriers. And so what ideas might there be for removing barriers? This is obviously not a complete list, but one thing that comes up often is a lack of visibility. People don't really know how much they're consuming. So establishing climate impact metrics, ideally coupled with performance, is very important. There can be a cost of change. Making climate aware development a priority means that you don't have to change. You might have processes established in the fab, and that can be difficult to change. But if you do it at the development phase, you start off with the process that you really want. And then finally, in terms of higher costs, the budget really can be motivated by business benefits. So I've mentioned some of them already, but just to reiterate, less dependence on material electrical supply chains, marketing opportunities, and workforce satisfaction are some of them. What I don't say explicitly here is a lot of newer workers want to work for companies that care about the environment and care about the planet. And so at some point it might be essential in order to get the workforce that you need. So lots of ways to remove barriers and lots of opportunities for us to focus on transforming the industry. And finally, sticking with the Lord of the Rings theme, Gandalf had advice for that small hobbit. And what he said was, all that we have to decide is what to do with the time given to us. I think that's something we can all think about. We have jobs, but, we can do them differently. And this is a wonderful time to be thinking and acting on the impulse to have less impact on the planet. So I've got some acknowledgements here, and I'd just like to thank you for your attention. And I always welcome questions. Feel free to get in touch with me later if you would like.